Welcome to part 4 of differential equations. In this section we'll be looking at applications of differential equations, and we're going to do so through 4 different examples. Each will be in their own video. So let's look at the first example. You've seen examples like these before. This one's dealing with velocity and displacement. The velocity of a particle is given by dx to t equals 4x minus 1, that's in meters per second, where x is the displacement. Initially the displacement is 3 meters. Find the equation for displacement in exact form. So we'll start off by writing our equation, dx to t, so that's just velocity, the change in displacement with respect to time, equals 4x minus 1. Now if the velocity was given in terms of time, we would just be able to go straight ahead and integrate. However, it's in terms of x, displacement. So what do we need to do with this thing? Well, if we reciprocate both sides, we can get to t dx, and we can flip the right hand side as well, 1 on 4x minus 1. Now we can go and integrate with respect to x. So we'll take the integral of both sides now. And what's the integral of this derivative? Well, it's just t. And now we need to integrate the right hand side. So when we look at this integral, and this is with respect to x, what are we going to do? Well, with a fraction where there's just x on the bottom, on the denominator, we should hopefully recognize that this is going to give us a log when we integrate. But this is not simply 1 on x, which would give us ln of x. We've got 4x minus 1 here, so we're looking at ln of f of x. What happens when we take the derivative of ln of f of x, when we derive this thing? Well, we get the derivative of the inner function over that inner function. In this particular case, right, we have 4x minus 1 as like our inner fx function. So what would the derivative of that be? So if we're saying that our fx is 4x minus 1, then we can see the derivative is 4. So preferably that's what we would like to see here. We would like to see a 4. So let's set it up that way so that it has what we would like. So we're going to rewrite this. We'll put 4 on the top and our 4x minus 1 on the bottom. However, this has just completely changed the question, and we can't do that, so we need to compensate. So we'll put a 1/4 out the front. Now that we have it in the form we like, we can integrate. So this is going to be ln of fx, which is 4x minus 1. However, remember when we're going back the other way, we need to take the absolute value. And finally, our constant of integration. Now we know from the initial question that we can work out this constant of integration. We were told that initially the displacement is 3 meters. So initially means when time equals 0. So at time equals 0, displacement equals 3. So let's go and substitute that information in. So when time equals 0, displacement, or x, equals 3. So we have 4 lots of 3, which is 12, and 12 take away 1 is 11, And we know that the absolute value of 11 is just 11. Now, just make sure my ones look like ones here. We've got a lot of absolute values and L for ln going on here. Okay, so 1/4 times log of 11 plus c, that's equal to 0. So therefore, we can see that our constant is negative 1/4 of ln 11. Alright, so let's rewrite our equation now, updated. So t is equal to 1/4 ln of 4x minus 1 plus this constant, which we know is actually a negative. So plus this negative value and minus 1/4 ln of 11. Alright, we want the equation for displacement. That's what we're after. So we actually want to make x the subject of this thing. So we have to rearrange to get x on the left hand side. So first of all, what can we do? Well, notice when we look at this that we have 1/4 as a common factor. So let's drag that out the front to make things a little bit nicer. Next, is there a way that we can combine these two different logs? So remember when we have log of one thing minus log of another, right? Whatever that base is, I'll just stick with ln, some ln A minus some ln B. We can use our log laws, which tells us that we can combine this. Okay, so we can combine these two into just the one log expression, and we're going to have ln. Now we need to still keep our exact values, our absolute values, sorry, for now. Alright, so this is looking a little bit better. Remember, we're trying to make x the subject. Giving ourselves a bit more room. Alright, so let's get rid of this quarter first of all. So we'll multiply both sides by 4. And then we need to think, okay, how do we get rid of this log? So we need to take the exponential of both sides. So e to the power of 4t will give us 4x minus 1 over 11. Now remember, we've seen this previously, we could keep the absolute values here, okay, and go and do the positive or the negative version, but it sort of works out the same either way, but definitely go and explore that yourself if you'd like. So multiplying both sides by 11. Really close now, we're going to add 1 to both sides. And finally, we'll divide by 4. And just swapping it around so that x is on the left. We have our 11e to the 4t plus 1, and that's all over 4. So there's part A done. Let's go on to part B. Sorry, before we jump into part B, I should just add, going back here, just to clarify, when we went from this step here with the absolute value to this step here, because we're dealing with an exponential where whatever we plug in here, this is only ever going to be positive, right? So that's why we can only focus on the positive version. So it is a little bit different to what we've seen previously, but this exponential can only be positive, so therefore the right hand side can only be positive. So that's why we don't need to consider the negative version of the absolute value. Okay, part B, find the exact displacement after 5 seconds. So here all we need to do is go, okay, using part A, where I have displacement in terms of time, I can just substitute in t equals 5. Now we want to express it in exact form, okay, so we don't need to go to the calculator or anything. We've got e to the power of 20, okay, so 4 times 5 when we substitute that in, so e to the power of 20 plus 1 all over 4. Now, because we're after a displacement, this is going to be in meters. Okay, nice and easy for that part. The final part of this example, part C, find the time when displacement is 10 meters. And we're going to find this correct to 2 decimal places. So now we are taking our equation from before, but we are substituting in x equals 10, because that's what we know. So our displacement x is 10, and we're solving for t. So we need to rearrange this so that t is the subject. So let's multiply both sides by 4. We get 40 equals 11 e to the 4t plus 1. We can subtract that 1 from both sides. Next step is to divide both sides by 11. Now switch things around here as well, so I'll get e to the power of 4t equals 39 over 11. Now to undo the exponential, we want to take the log of both sides. When we do that, we have 4t equals the natural log of 39 on 11. And finally, we're going to divide by 4. Alright, once we get to this stage, it's time for the calculator. So, natural log 39 over 11. That's what we're taking there, but then that is all over 4. So we get correct to 2 decimal places, t is equal to 0.32. And because it's a quantity, we want the correct units, and so that will be 0.32 seconds. And that finishes us for our first example.